Alright, so this is the second of 3 videos on continuous functions for Math 1560 Calculus 1 at U of L for fall 2017. And in the previous video we defined what it means for a function to be continuous, and now we're going to explore some of the properties that continuous functions have. So here's a list of algebraic properties that continuous functions have, and as you might expect, all of these follow from the corresponding algebraic properties of limits, right? So the sum of continuous functions is continuous, the difference of continuous functions is continuous if you multiply by a constant, if you multiply two functions, if you take a quotient, well, as long as the function you're dividing by is non-zero, right? If you combine continuous functions in this way, you get another continuous function. And all of these just follow directly from the limit properties. Right? Because we know that the limit of a sum is the sum of limits and so on, right? So for example, if we know that the limit as x approaches a of f of x equals f of a, and we know that the limit as x approaches a of g of x equals g of a, right? So if we know this, if these are our hypotheses, these two conditions here, then you can say, well, what would happen if I took the limit as x approaches a of f of x plus g of x? Well, we would get the limit of f of x plus the limit of g of x, so we would get f of a plus g of a. So we get the value of the function at that point. Right? And similar arguments are going to get you all the rest of these properties. So this is good because it means that once you have a few examples of continuous functions, you can start building up other examples of continuous functions. Right? And you get all of these guys here. So for example, polynomials. Why do we know that polynomials are continuous? Well, let's say that my polynomial function, let's say it looks like, say, a(n) x to the n down to, let's say, a1x plus a0. Remember, every polynomial involves powers of x multiplied by some constants and then added together, right? So it might be a linear function, it might be quadratic, cubic, right? There might be an x squared, x cubed term in here. I'll try to write down a general polynomial. So if you try to take the limit as, let's say, x approaches c of p of x, right? Well, the limit laws say you can take the limit term by term, right? Limit of a sum is the sum of the limits. Okay, a1x. And then the last term is just a constant. We know the limit of a constant is a constant, right? And then we know that, you know, these constants here, they can come out of the limit. You can pull constants out. And one of the other basic limit properties we had is that if you take the limit of x to the n, you just, you know, whatever the value is, in this case c, you would just get c to the n. So you get, just using the basic algebraic rules for limits, you get an times c to the n, and so on down to a1 times c. And that's exactly what you would get if you just plug x equals c into the polynomial. In other words, you get your function value, right? So a polynomial function is continuous at every single real number, right? They're continuous for all real numbers. Rational functions, well, we know that a rational function is just one polynomial divided by another, and so again, the limit laws, there's a quotient rule for the limit properties, and so as long as that polynomial on the bottom is not equal to 0, then the limit properties apply there. So as long as you stay away from the zeros of the denominator, your rational function is continuous. And of course, the zeros of the denominator are exactly the points that don't belong to the domain. So radical functions, we won't really give a proof that it works for roots, but it does work for roots. For the trig functions, actually, if you go back and you look at the first video on trig limits, you'll find that we did show in the first trig limit video, we showed that the limit as x approaches a of sine x equals sine A. We actually gave a proof of that. A similar argument works for the cosine function, and then of course tan is sine over cos, so you can use the quotient property for limits to get that one. Exponential and logarithmic functions are also continuous, but we are not going to give a proof of that in this course. Okay. And the other thing that you want to look at in terms of properties of continuity is what happens with composition, right? We said what happens with addition, multiplication, division, these things, but the other really important operation on functions is composition, plugging one function into another. And so the first thing is that if you have two continuous functions and you compose them, you get a continuous function. So that means, that, for example, since we know that f of x equal to e to the x and g of x equals x squared, we know that these are continuous. We know that if we do f of g of x, which would be e to the x squared, right? So now we use composition to build more complicated functions like this guy. We know now that that is also a continuous function. Okay. Continuity also plays a role in limits, right? So if you want to take the limit of a composition and you know that that outside function is continuous, you're allowed to bring the limit inside. And this justifies some of the limit rules that we saw before that were stated without any sort of justification. So for example, if I was doing something like the limit as, and let's say x goes to 0 of, let's say, I don't know, the natural log of x squared plus 1, I can say, well, that's the natural log of the limit x going to 0, x squared plus 1, and so that's the natural log of, well, this limit inside is just 1, right, because x squared is going to go to 0, and the natural log of 1 is equal to 0. So I can now do limit calculations like that, making use of continuity. But it is important that you kind of demonstrate some awareness of continuity when you do this sort of thing. When you bring a limit inside, you are relying on the fact that you know this outside function, something like the natural log, you know that that function is continuous. All right, so we're gonna do one more video on continuity. We're gonna cover an important theorem about continuity called the intermediate value theorem, and then we'll be ready to move on to derivatives.